Hey guys, this is Mr. Ward. Welcome to Matrices Day 3, Unit 4. Shortened examples today, only 3, but as you can imagine, they're pretty time consuming. Let's see if we can try to get all these done in about a 15-minute window. All right, so the warm-up is we're going to use Gaussian elimination on the matrix and back substitute. We're actually not going to do that. We're going to start with the next one because it's a 2x2, and I thought that'd be a great way to warm up. So, first thing, let's use our words. Let's create a 2x3 augmented matrix. 1, 2, 7, 2, 1, 8. Everybody should go, yeah, that makes sense. The process we're going to use is Gaussian elimination. Don't worry about this word Jordan yet, okay? And that means we're going to obtain a row echelon form matrix, okay? A 1 in the first row, first column, a 0 in the second row, first column, and a 1 in the row 2, column 2 position. And it looks like we got at least a good start here. We got a 1 where we want it. Now I want a 0 where the 2 is, but I can do that pretty easily. Row 2 minus 2 row 1s. 1, 2, 7. 2 minus 2, 0. 1 minus 4, negative 3. Don't panic that we lost that 1 to get to negative 3 because we got the 0. That's going to be more important to us. 8 minus 14 is negative 6. We've got our 1. We've got our 0. Now we got to get that last 1. And again, with zeros in the row, that's when we multiply. So I think our third iteration will actually do it. We're leaving row 1 alone. We're going to take row 2 and multiply by negative 1/3. And I bet you that's what a lot of you thought. 0, 1, 2. It is now in row echelon form. I know that x plus 2y equals 7, y equals 2, and I can back substitute. But here's what you should be thinking. Mr. Ward, what if, just like row 2 has a 0 here, and that 1 tells me what y is, what if we got a 0 here, and that would tell me what x is? And there's a name for that. When it's all 1s and 0s, that's called reduced row echelon form. So just like row echelon looks like this, 1, 1, 1, I'll do a 3 variable matrix. It's a little bit more substantial. And it requires back substitution. A reduced row echelon form matrix, or RREF, and again, that's on our calculator in a couple days, has the main diagonal 1, these are 0, and these are 0, which tells me what x equals, what y equals, and what z equals, without any back substitution. And just like Gaussian elimination got us to row echelon, a mathematician named Jordan added some other additional steps on to create Gauss-Jordan elimination, and that uses the elementary row operations to obtain our REF, solving for x, y, and z, and we don't need to back substitute. So the reason why I did that 2x2 is because now we're going to do that extra step. We're going to take this blue matrix and we're going to do one more thing to it. And that is, I'm never touching row 2. Why? Because that tells me y equals 2. But what I want to do is I want to get a 0 where the 2 is. And how am I going to do that? I'm going to go row 1 minus 2 row 2s. 1 minus 0 is still 1. 2 minus 2 times 1 is 2. 2 minus 2 is 0. Just what I wanted. 7 minus 2 times 2, 7 minus 4 is 3. Now it's in reduced row echelon form. Y equals 2, x equals 3. That's the ordered pair new process. All right, so let's do it again. We're going to do Gauss-Jordan. We're going to get it into reduced row, and then we're going to do a 3x3. Let's create our 2x3 augmented. 3, 1, 2, 2, negative 4, 20. And what do we want? We want it to look like this. 1, 0, something, that's X. 0, 1, something, that's Y. X equals, Y equals. All right. I want that 1 up in the row 1, column 1 first. How am I going to do it? I bet you some of you guys are getting the hang of this. Row 1 minus, oh, sorry. I think my smart board's a little bit off-oriented. Row 1 minus row 2. 3 minus 2 is 1. 1 plus 4 is 5. 2 minus 20 is negative 18. Copy this down. I'm 1/4 of the way there. I got my 1. I want a 0 where the 2 is. Iteration number 2. 1, 5, negative 18. Row 2 minus 2 row 1s. 2 minus 2 is 0. Negative 4 minus 10 is negative 14. 20, 2 times 18 is 36. 20 minus 36. Oh, did I do that right? 18 to 36. Oh, pardon me. Minus 2 times negative 18 is 20 plus 36, which is 56. Got it. All right, I have my 0. So now I'm going to turn that negative 14 into a 1. 1, 5, negative 18. How am I going to do that? I'm going to multiply row 2 by negative 1 over 14 of row 2. 0 times anything is 0. Negative 14 divided by negative 14 is 1. 56 divided by negative 14 is negative 4. I know what y is. Could I back substitute? I could, but why? Let's get one more iteration, one more step. Let's get rid of that 5. Let's get it into reduced row. I'm never touching row 2 again. What am I going to do to row 1? And you can pause this, guys. Figure it out on your own. Stop. Do something. However you learn best. Row 1 minus 5 row 2s. 1 minus 0 is 1. 5 minus 5 is 0. Negative 18 plus 20 is 2. The solution is x equals 2. Y equals negative 4. Beautiful. Beautiful. And again, process is everything. And the rules that I like to remember is this. In my steps, using zeros to keep numbers and ones to get rid of numbers. All right, we're about 9 minutes in. I think we can get our last example done and do it all in less than 15 minutes on our video here. All right, last one. We have a 3-variable, 3-equation system. We're going to get it into augmented 1, negative 2, 3, 9, negative 1, be careful, 3, 0, negative 4, 2, negative 5, 5, 17. And we want to get that into reduced row echelon form. A lot of 1s in the diagonal, and all the remaining are zeros. So that gives me x equals y equals z equals. Order. I'm going to do that first. I'm going to do this second. I'm going to do this third. And I'm going to do these last. All right, so I want a 1 where the 1 is. Got it. Leaving row 1 alone for a little while. I want a 0 where the negative 1 is. Got it. Row 1 plus row 2. Negative 1 plus 1 is 0. 3 minus 2 is 1. 0 plus 3 is 3. Negative 4 plus 9 is 5. Row 3 minus 2 row 1s. 2 minus 2 is 0. Negative 5 plus 4 is negative 1. 5 minus 6 is negative 1. 17 minus 18 is negative 1. If this sounds familiar, it should. It's an example we did yesterday. We're just practicing the steps, doesn't matter, but we're getting it into reduced row echelon form. So what do we got? I'm going to put blue stars here. Got it, got it, got it, got it. All right, next, I want a 0 where the negative 1 is in row 3. My red iteration. 1, negative 2, 3, 9. 0, 1, 3, 5. Row 3 plus row 2. 0 plus 0 is 0. Negative 1 plus 1 is 0. 3 plus negative 1 is 2. 5 minus 1 is 4. I'm now going to divide row 3 by a half. You guys are probably faster than me now. 0, 1, 3, 5. A half of row 3. 0, 0, 1, 2. I am now in row echelon, but I don't want to back substitute. I want to get 3 more zeros. Here's how I do it. New iteration. I'm never touching row 3 again, ever. I'm going to take row 2, and I'm going to subtract 3 row 3s. The 1 in row 3 will get rid of the 3 in row 2, and the zeros will keep the other 2. 0 minus 0 is 0. 1 minus 0 is 1. 3 minus 3 is 0. 5 minus 6 is negative 1. Sorry, I don't like that one there. Sorry, I'll write it the normal way. Negative 1. So what do we know? We know x equals, we know y equals, and we know z equals. Now we got 2 more numbers to get rid of. 2 more iterations. Row 1 minus 3 row 3s. 1 minus 0 is 1. Negative 2 minus 0 is negative 2. 3 minus 3 is 0. 9 minus 6 is 3. I'm almost home. I know what y is. I know what z is. I'm going to find x on this iteration right here. I'm going to use row 2 to get rid of that negative 2. Row 1 plus 2 row 2s. 1 plus 0 is 1. Negative 2 plus 2 is 0. 0 plus 0 is 0. 3 plus negative 2 is 1. 0, 1, 0, negative 1. 0, 0, 1, 2. So what did I do? I got the matrix. I used Gauss Jordan elimination to get the matrix into reduced row echelon form, hence solving x equals 1, y equals negative 1, z equals 2, ordered triple, 1 comma negative 1, 2. The only ordered triple that would solve all 3 of these equations simultaneously. Or again, the intersection of the 3 planes in space, the one unique ordered triple. All right, guys, got day 3 done. Well done. If you need to look at it more than once, by all means do. This whole idea of using a matrix, box of numbers, really interesting. And again, process is everything. All right, have a great day. We'll see you.